Hello, everyone. Welcome. This is my another video of machine learning landscape. In this presentation, we will talk about a high-level overview of the overfitting and underfitting problem. This is a common problem when building the machine learning model, as it is a high-level overview, so we won't talk any math involved with it. We will try here to improve the fundamental understanding over the topic. In a machine learning project, we gather data in a training set and feed the training data to a learning algorithm. If the algorithm is model-based, it tunes some parameters to fit the model to the training set, and then hopefully, it will be able to make good predictions on new cases as well. If the algorithm is instance-based, it just learns the examples by heart and uses a similarity measure to generalize to new instances. Here, the system will not perform well if our training set is too small, or if the data is not representative and noisy with their relevant features. Lastly, our model needs to be neither too simple, because it causes the algorithm underfitting, nor too complex, because it causes the algorithm overfitting. Since our main task is to select a learning algorithm and train it on some data. So, the two things that can go wrong, the bad algorithm and the bad data. Let's start with examples of bad quality data. If our training data contains a lot of errors, outliers, and noise, then it will make it harder for the system to detect the underlying patterns, so the system will less likely be to perform well. It is often well worth the effort to spend time cleaning up the bad quality data. The truth is, most data scientists spend a significant part of their time doing just cleaning up the training data. The bad quality data involves the visibly outliers. If some instances are visibly outliers, then we can simply discard them or try to fix the errors manually. Missing features. If some instances are missing a few features, we must decide whether we want to ignore this attribute altogether, or train one model with the features and one model without it, and so on. Irrelevant features. Bad quality data also involves irrelevant features. Our system will only be capable of learning if the training data contains enough relevant features, and not too many irrelevant ones. The critical part of the success of a machine learning project is coming up with a good set of features to train on. This process is called feature engineering. The task involved in feature engineering are to select the most useful features to train on among existing features, combining existing features to produce a more useful one, creating new features by gathering new data. So, we have looked at many examples of bad quality data. Now let's look at the bad algorithms that cause underfitting and overfitting problems. Generally, for a machine learning model, we split our data into different sets. For example, we might split the data into two different datasets, such as training set. Using this we train our model. And using the test set, we test our model that how well it can perform. Sometimes we also split the dataset in the development set. On that we test model performance on different algorithms. To avoid wasting too much training data in test and development sets, the common technique is to use cross-validation. The training set is split into complementary subsets, and each model is trained against a different combination of these subsets and validated against the remaining parts. Once the model type and hyperparameters have been selected, a final model is trained using these hyperparameters on the full training set, and the generalized error is measured on the test set. To read more about cross-validation, please read our blog post. I have put the link in the description. Let's talk about the high bias problem and the underfitted dataset. The word bias means inclination against one person or group, especially in a way considered to be unfair. In machine learning, the idea of having bias was about the model is giving more importance to some data points to generalize better for the larger dataset with various other attributes. Bias algorithm generalizes the model better and makes it less sensitive to some single data point. A linear model such as regression fit is highly biased to some data points that cause the underfitting problem of the dataset. The model shows bias to some data points, and some data points are completely ignored. As we can see in the graph, that the regression fit line has become too generalized the linear model. It means the algorithm draws a too general linear decision boundary between data points. So, the boundary it is highly biased to some data point, which means giving some data points more importance, and some data points are just completely ignored by the model. Here, looking at the training set error, we can say how the model fits our training data. If the training set error is high, then it tells us that the algorithm has the high bias problem, and the model is underfitting the dataset. After building our initial model, the first thing we will check, does the algorithm has a high bias or high variance problem? If we find a high bias, we need to look at the performance of the training dataset. The highly biased model doesn't fit the training set that well and causes underfitting dataset. So, the following tasks can reduce underfitting problem of the dataset. Selecting a more powerful model with more parameters. Feeding better features to the learning algorithm by feature engineering. Reducing the constraints on the model by reducing the regularization hyperparameter. For deep learning model, we can reduce high bias by initiating a bigger network, using some more advanced optimization algorithm and train the algorithm longer. Or we can try other neural network architecture that is better suited the dataset. Now, let's talk about the algorithm that covers high variance data which causes the overfitting problem. If there is a high variance in the dataset, a high degree polynomial fit model tries to fit the data perfectly. So this causes overfitting problem. Overfitting occurs when a machine learning model performs well on the training dataset, but the loss function increase on the test set. It means accuracy increased significantly on training data, but it doesn't perform that well on testing data. So, the model becomes too specialized to solve the training data. Because a high degree polynomial fit model strongly overfits the training data. Hence the model performs worse validating the test data. As we can see in this graph, that a high degree polynomial fit model has specialized over the training dataset. Or, we can say it is perfectly fitted, or overfitted the training set by completely separating two different types of decision sets, A's and B's. So, accuracy increased significantly on the training dataset, but it doesn't perform that well on the testing data. Here we have listed a train set error is 5%, and the test set error is 20%. So the difference between train set error and test set error is 15%. Remember that, higher the difference between the train set error and test set error, tells the algorithm has a high variance problem. And, it overfitted the training data. So, the accuracy increased for the training data, but the loss function increased for the test data. Let's see the possible solutions to reduce the overfitting problem. As we have seen, that overfitting happens when the model is too complex relative to the amount and noisiness of the training data. So, the possible solutions are to simplify the model by selecting one with fewer parameters. For example, choosing the linear model rather than a high-degree polynomial model by reducing the number of attributes in the training set to gather more training data, and reducing the noise in the training data, such as fixed data errors and remove the outliers. There is also a concept of bias-variance trade-off, although this is not the topic of discussion for this presentation. So, let's go a little over that. The goal of any supervised machine learning algorithm is to achieve low bias and low variance. Consequently, the algorithm should achieve good prediction performance. So here the concept is, linear machine learning algorithms often have a high bias, but low variance. On the other hand, nonlinear machine learning algorithms often have low bias but high variance. We have almost come to the end of our discussion. I also wanted to talk about regularization and hyperparameter to optimize an algorithm. But for the time limit of this video, I could not cover these topics in this presentation. But this can be the topic of our next video. We have so far discussed that to build a good prediction model, we need a good dataset and a good algorithm. So, two things can go wrong. The bad dataset, and a bad algorithm that causes overfitting and underfitting problem. We also have discussed how to get rid of bad data, and chose the right dataset for an algorithm, and how to reduce the overfitting and underfitting problem. So, at the end of this presentation, we can say, a machine learning model is a simplified version of the observations. The simplifications are meant to discard the superfluous details that are unlikely to generalize to new instances. However, to decide what data to discard and what data to keep, we must make assumptions. For example, a linear model assumes that the data is fundamentally linear. So, if we make absolutely no assumption about the data, then there is no reason to prefer one model over any other. For some datasets, the best model is a linear model, while for other datasets, it is a neural network. But no model is a priori guaranteed to work better. For simple tasks, we may evaluate linear models with various levels of regularization, and for a complex problem, we may evaluate various neural networks.